For many years, scientists have been working to create machines that can speak like humans. The journey has been long and filled with numerous challenges, but the goal has always been to achieve a level of speech synthesis that is indistinguishable from human speech. This field of study is called speech synthesis. It encompasses a wide range of techniques and technologies aimed at generating human-like speech from text. Early attempts at speech synthesis, like concatenative and parametric synthesis, had limitations. These methods were groundbreaking at the time, but fell short of capturing the true essence of human speech. Concatenative synthesis involved stitching together small recorded speech fragments. This method relied heavily on pre-recorded data, making it difficult to produce fluid and natural-sounding speech. This method often resulted in robotic and unnatural-sounding speech. The transitions between the stitched fragments were often noticeable, breaking the illusion of a seamless human voice. Parametric synthesis, on the other hand, used mathematical models to generate speech sounds. These models allowed for more flexibility in generating speech, but came with their own set of challenges. While more flexible, it often lacked the naturalness and expressiveness of human speech. The generated speech sounded flat and lacked the emotional depth that characterizes human communication. These traditional methods struggled to capture the nuances of human speech. The subtle variations in pitch, tone, and rhythm that make speech sound natural were often missing. They often sounded monotonous and lacked the natural variations in pitch, tone, and rhythm. This monotony made the speech sound artificial and unengaging. These limitations highlighted the need for a more sophisticated approach to speech synthesis. Researchers began exploring new methods and technologies to overcome these challenges. This is where Tacotron, a revolutionary deep learning-based system, comes into the picture. Tacotron leverages the power of neural networks to generate speech that is remarkably close to human speech, in terms of naturalness and expressiveness. Tacotron, developed by Google AI, represents a significant leap forward in speech synthesis technology. It leverages the power of deep learning, a type of artificial intelligence that enables machines to learn from vast amounts of data. Unlike traditional methods, Tacotron takes a fundamentally different approach. It is an end-to-end system that learns directly from text and corresponding speech recordings. This means that Tacotron can learn the complex mapping between text and speech without relying on handcrafted rules or explicit pronunciation dictionaries. This end-to-end learning capability is key to Tacotron's ability to produce highly natural and expressive synthetic speech. At the heart of Tacotron's architecture is its ability to convert text into a visual representation of speech called a spectrogram. A spectrogram is a graphical representation of sound frequencies over time, essentially capturing the acoustic features of speech. Tacotron uses a deep neural network, a complex structure inspired by the human brain, to learn the relationship between text and its corresponding spectrogram. Once Tacotron generates the spectrogram, it is then passed through a separate component called a vocoder. The vocoder is responsible for transforming the spectrogram back into audible speech waveforms. This two-step process, from text to spectrogram to speech, allows Tacotron to generate highly natural and expressive synthetic speech. Tacotron's deep learning approach offers several advantages over traditional speech synthesis methods. Unlike traditional methods that rely heavily on predefined rules and manual feature engineering, Tacotron leverages the power of neural networks to learn directly from data. This allows it to produce more accurate and natural-sounding speech. Firstly, Tacotron's ability to learn directly from data allows it to capture the nuances and subtleties of human speech that often eluded previous methods. This means it can understand and replicate the intricate patterns of intonation, stress, and rhythm that make human speech so unique. This results in significantly more natural and expressive synthetic speech, making interactions with AI systems more pleasant and engaging for users. The difference is especially noticeable in applications like virtual assistants and automated customer service, where naturalness and expressiveness are crucial. Secondly, Tacotron is highly flexible and can be trained to synthesize speech in different languages and voices. This flexibility is a game changer for global applications, as it allows for the creation of multilingual systems that can cater to a diverse user base. This adaptability makes it a versatile tool for various applications, from voice assistants and audiobooks to language learning apps and beyond. The ability to switch between different voices and languages seamlessly enhances user experience and broadens the scope of potential uses. Thirdly, Tacotron's end-to-end nature simplifies the speech synthesis pipeline. Traditional methods often involve multiple stages and complex processes, but Tacotron streamlines this by integrating everything into a single cohesive model. It eliminates the need for complex linguistic rules and hand-engineered features required by traditional methods. This not only reduces the time and effort needed for development, but also minimizes the potential for errors and inconsistencies. This simplifies the development process and allows for easier updates and improvements to the system. As a result, developers can focus more on innovation and less on troubleshooting, leading to faster advancements in speech synthesis technology. Section 5. Key research findings. Pioneering work in speech synthesis. The development of Tacotron has been guided by significant research findings in the field of deep learning and speech processing. This innovative model represents a major leap forward in the way machines can generate human-like speech. By leveraging advanced neural networks, researchers have been able to create a system that not only understands the nuances of human speech, but can also replicate them with remarkable accuracy. A seminal paper by Wang et al., published in 2017 titled Tacotron Towards End-to-End Speech Synthesis, laid the foundation for this revolutionary approach. This paper was a game-changer, providing a comprehensive framework for developing speech synthesis systems that could operate end-to-end, from text input to audio output, without the need for intermediate steps. The paper presented the initial Tacotron model and demonstrated its ability to synthesize speech with unprecedented naturalness. The researchers showcased how the model could generate speech that was not only intelligible, but also carried the natural rhythms and intonations of human speech, making it sound more lifelike than previous models. The researchers highlighted Tacotron's ability to learn complex pronunciation patterns, handle variations in speaking styles, and produce speech that is often indistinguishable from human recordings. This capability was a significant breakthrough, as it meant that the model could adapt to different voices and accents, making it highly versatile for various applications. This work marked a turning point in speech synthesis research, paving the way for further advancements in the field. The success of Tacotron has inspired a new wave of research and development, leading to even more sophisticated models and applications that continue to push the boundaries of what is possible in speech synthesis technology. Tacotron's impact extends beyond the realm of research and into various real-world applications. One of the most prominent applications is in virtual assistants and voice-enabled devices. Virtual assistants like Google Assistant, Amazon Alexa, and Apple's Siri rely on high-quality speech synthesis to interact with users. Tacotron's ability to generate natural-sounding speech makes these interactions more engaging and human-like. Another important application is in accessibility technologies. For individuals with speech impairments, Tacotron-powered speech synthesizers can provide a voice. This can significantly enhance their ability to communicate and interact with others. Tacotron's natural-sounding speech synthesis makes it a valuable tool for promoting inclusivity and improving the lives of people with disabilities. Despite its remarkable capabilities, Tacotron is not without its limitations. One challenge is the computational resources required to train and run the system. Tacotron models require vast amounts of data and significant processing power. This can limit its accessibility and feasibility for certain applications. Another challenge is ensuring the consistency and accuracy of pronunciation, especially for rare words or complex linguistic structures. Tacotron may still produce mispronunciations or unnatural inflections in certain cases. Researchers are actively working on addressing these limitations by developing more efficient training methods and improving the model's ability to handle complex linguistic phenomena. The rise of highly realistic AI-generated speech, like that produced by Tacotron, raises important ethical considerations. One concern is the potential for misuse of this technology. Malicious actors could use Tacotron to generate fake audio recordings, impersonate individuals, or spread misinformation. This underscores the need for safeguards and ethical guidelines to prevent the misuse of AI-generated speech. Another ethical consideration is the potential impact on employment. As AI-powered speech synthesis becomes more sophisticated, it could potentially displace human voice actors in certain domains. It is important to consider the societal implications of such advancements and ensure a responsible and ethical transition. The field of speech synthesis is constantly evolving, and Tacotron has laid a strong foundation for future advancements. Researchers are actively working on improving the efficiency, robustness, and expressiveness of Tacotron models. One area of focus is developing multilingual and cross-lingual speech synthesis systems. Such systems would be capable of generating natural-sounding speech in multiple languages, further breaking down communication barriers. Another area of research is enhancing the emotional expressiveness of synthesized speech. This involves developing models that can accurately convey emotions like joy, sadness, anger, and surprise in the synthesized voice. These advancements promise to make AI-driven communication even more natural, engaging, and impactful.